Again, I won't taking the whole class for the lecture. I know you guys are hard, so I will talk about like 1 hour. And in the next class, we're still in the lab time. We're still finish the lab 15. Remember, we did the 2 titrations, but we didn't do the calculation, right? The purpose of the lab 50 is try to figure out the concentration of your unknown solution, the solution that you prepared, right? You don't know what exactly the concentration that the solution you prepared. So we're going to, based on the titration, the results, to figure out the concentration. And if we do have more time, I would like to use in the lab time to review the exam 3. Okay, yeah. Okay, so let's talk about what we review what we learned last time. Okay, last time we talked about the light. Okay, first we talk about electromagnetic radiation, and we know electromagnetic radiation is a wave. It's a wave. Okay, but when we extend that, it's also a particle. So last time we talked about visible light is has a wave and a particle duality. But we can extend more, not just the visible light. All the electromagnetic radiation has the wave and the particle duality. Okay, or has a wave and particle duality. And once we talk about a wave, then the wave is going to have several parameters we need to talk about, right? So they're going to have the wavelength, which is we call the lambda, and they also has a frequency. This is what we call the nu. It pronounced like a nu. The nu, the frequency is hertz. It's talking about how many times this wave will repeat in 1 second. How many times this wave will repeat in 1 second. Okay. And also the last time we talked about amplitude. The amplitude is talk about the distance from the baseline to the highest peak. And this is the amplitude that we talk about. We're using capital A to represent. Amplitude actually is also a wave, is a length. So in general, we talk about the relationship between those 3 parameters. Lambda multiply the frequency, it should be equal to the speed of light. The c is the speed of light. But the capital A, the amplitude is independent. Okay, so it doesn't matter how you change the amplitude or how you change the amplitude, it's not going to affect the frequency and the wavelength. Or if you change the frequency or the wavelength, you're not going to change the amplitude. So those 2 are independent, separate to each other. But if you have a higher wavelength, then you're going to have a smaller frequency. If you have a smaller wavelength, then you're going to have a higher frequency. So those are the relationship. And we also talk about a little bit of history about how the people find the particle, the visible light is the wave and also the particle, right? So first we talk about the Thomas Young find the visible light is a particle, is a wave, based on the experiment. It's called the double slit experiment. The double slitting experiment, it talk about if we have a visible light, and this is a light source. So I think it's light source, and if we have a double slit, shows over here, and then one, the light is penetrate through the slit, then they're going to have interference under a background. So they are going to have some light, bright light, dim light, bright light, dim light. And this is the very bright part is what we call the constructive interference. And the dim part is what we call destructive interference. So that means this is the typical property that shows in the wave. So that's why they prove light is a wave. But later, the Albert Einstein also find another property. It's called a photoelectric effect, which he find, okay, if we have a light and shoot on the surface of a metal, some of the metal will eject the electrons out. Well, this kind of property is just like the impact some object, heavy matter object shooting on the surface of some of thing, and then they have something eject out. And generally, this is a property of a particle, not a property of a wave. A wave cannot doing this. So that means he find, well, so he has the idea, well, all of those, the light is just like a discontinued particle. And this particle shoots on the surface of the electron, surface of the metal. And if the particle has carry enough energy, if this particle carry enough energy, then it will knock the electron out. But of course, if the particles do not have enough energy, and then it didn't do anything. Okay, it didn't do anything. Okay, so this is what we call the photoelectric effect. And also, one of the application is just the solar panel. The solar panel generally is just the visible light and shooting on the surface of the solar panel. The solar panel made by the specific material. And then once the light shoot on the panel, and then they knock the electron out. And once you collect those electrons, and then we're just restore. We will just keep those electrons, and then the electricity will generate. This is generally what happens. Electricity is just the current of electrons. Okay, electricity is just current of electrons. Once you're stored those electrons, then generally you store the electricity. This is what happens for the solar panel. Okay, yeah. So this is one of the typical application for photoelectric effect. But you see, we talk about the solar panel is a clean energy. Yes, it's a clean energy. But the point is the efficiency to convert the light to the electricity is really weak. The percentage probably like 10%, 20%, and then that's it. Because you need to understand, when the photon, those small particle, what we call the photon, when the photons shoot on the surface, they're going to lose the energy. Why? When you shoot on the surface, it's not completely convert the electron eject out. You need to shoot on the surface, and some of the energy will be converted to the work that's knocking the electron out. So that's why the conversion effect is really, really low. So that's why sometimes, the scientists still try to find some of the material. Find the material to try to making the more efficient. which is maybe convert to like 30% or 40%. I mean, if you can restore the energy from 30% to 40%, that's a lot of energy. But right now, it's still very expensive and low efficiency. That's why. Okay. So you see, the material science actually has a very bright future because the scientists try to find it. Right now, even for the battery, the scientists still try to find a good material to making a better, efficient battery. Yeah, this is also, so if you're interested for the material science, and then you can, I mean, just stick with this for your future career. Well, so that's why, I mean, when we talk about photon, those are small particle, and the photon, they carry of the energy, right? But the point is, each of the photon will carry the same energy. You see, the visible light is just like a photon, discontinuous photon shooting on the object. And each of the photons, generally, they are carrying exactly the same energy. Okay, it doesn't matter how many photons you have, they always carry the same energy for a certain electromagnetic wave. Because the energy of the photon is by definition is h times nu. Okay, so the h is what we call the Planck constant. And nu is the frequency. In another word, if you already know what kind of the frequency or the wavelength of the certain electromagnetic wave, you should already know what is the energy for the photon, because the energy is proportional to the frequency. So this is another relationship I hope you understand. So now we have three things. Then you need to find a relationship, which is energy, frequency, and the wavelength. So those three are related to each other, right? We talk about if you have a higher wavelength, then you should have a lower frequency. And meanwhile, you should have a lower energy of those photons, the photon energy of the photon. That makes sense, right? But if you have a lower wavelength, then it will give you a higher frequency, and then it will give you a higher energy. Okay, so that is why we talk about some of the wave, the electromagnetic wave is harmful, some of it is not harmful. It's based on their frequency. Okay, higher frequency give you higher energy, then obviously they are harmful. Okay, lower frequency give you a lower energy, then they are not harmful. That makes sense, right? Okay, so this is generally what we talk about last time. Okay, this is what we talked about last time. And today we're going to talk about something else. Okay, the one thing we're going to talk about is called hydrogen spectrum. Hydrogen, you probably already learned this before. Okay, let's just review it. Hydrogen emission spectrum. This is emission. Hydrogen emission spectrum. So generally, what is the spectrum? Spectrum is just a wavelength with a broad range. Then this is what we call the spectrum. If you're looking at the sunlight, and this is the spectrum that the sunlight gives to us. So this is the spectrum that sunlight gives to us, which is a continuous spectrum. You can see all the range of the color from red to the violet, right? Red, you have the red, orange, yellow, green, teal, which is the range over here, and the blue, and you have purple and the violet. So that's generally is the range of the visible color, right? And this is what we call the continuous spectrum. But for a scientist to realize if we have the hydrogen in the gas tube, and generally this is a hydrogen gas in the gas tube. And then we apply very high voltage on the gas tube, and then the hydrogen will emit the light. Well, just to let you know, the color is not right. We will see in the lab, okay? When the hydrogen emits, the color is not blue. Its color is a violet. It's a purple color, okay? It's a mixture of those color all together. And then you will see when this light goes through the single slit, then the slit light will travel through the prism. Since the different color, different wavelength of the light or the emission electromagnetic wave, they travel with the different speed. When they go through the prism, they're going to reflect on the light on the background in the different position. Okay, so that is why. But when we can see only just 4 different light over there, line, 4 different lines shows up there. It's not exactly the continuous spectrum. It's a discontinuous spectrum. So this spectrum, we give it a special name. We call this as a line spectrum. So this is a line spectrum. The line spectrum actually is what exactly shows for the hydrogen, and the different material will give you the different spectrum, but hydrogen will give you some spectrum like this. And this is a very interesting because suppose has like a continuous spectrum, but for the hydrogen, these single elements, they give you this spectrum. Not a continuous. And then, and since at 1800s, at that time, people can identify, can measure what is the wavelength for each of the light, okay, based on the travel speed when they go through the prism. So they can calculate what is the wavelength for each of this. And then they figure out, wow, this wavelength can fit in one of the equation, which is 1 over the wavelength. The lambda should be equal to a constant, and then time 1 over n1 squared minus 1 over n2 squared. This is very interesting. So people figure out, okay, we have the equation shows up there, and then those wavelengths can fit into this equation, and also the n1 and n2 are equal to a whole number, and there must be a whole number. And this is very interesting because in the nature, not so many things can fit for a whole number. They all, every time they're, they follow some of the like fractions or decimal. They definitely has a decimal. If you're talking about the whole number, usually this is artificial or man-made, right? Yeah. But in nature, this is also fit. And then later, the scientists also find out, okay, so if we want to have this, the red color, then the n equal to 1 should be 2. The n equal to 2 should be 3. Then we fit this color. If we got like a green gray, and this is like a turquoise color, the n1 should be 2 and n2 should be 4. And this one, the blue violet color, n1 should be 2 and n2 should be 5. For the violet color, the n1 should be 2 and n2 should be 6. Well, that's going to be very, very interesting. So they find out this equation. They find that the wavelengths can fit into this equation. And also we find that the n1 and n2 must be a whole number to solve this problem. But they haven't idea. They do not have any idea what's going on, why we have these things happen. And then that's why the Bohr find his model and expand those things. I think you're heard of, anyone heard of the Bohr model before? You heard of this, right? Some of those heard of this, the Bohr model. But just to let you know, Bohr model is not exactly the model. It's not what happens. Okay, and it's not what happens like what we know right now. Right now, we talk about the quantum mechanics, but the Bohr model has some of the property that is similar like what we learned. So that's why we talk about this. The Bohr talk about, okay, the nucleus is in the middle and the electrons is orbit around the nucleus, just like the planet orbit around the sun. So they talk about a 2D structure. It's not talk about 3D. So nucleus is in the middle, and then we're going to have the orbit. I'm not going to write the orbit. The orbit will be very, very big. So I'm going to just write it like this. Okay, I'm writing the distance between each of the orbits in purpose. So the first orbit is N1, the second one is N2, and N3, N equal to 4, N equal to 5, N equal to 6, and the last one is N equal to 7. But more than this, they can go to infinity, N equal to infinity. Okay, yeah, but right now we're just writing the 7 of those orbits. So what he talk about the electrons usually is orbit. This is talk about hydrogen, since we only have one electrons in the hydrogen atoms, right? So we just discuss what happened for this single one electron. Okay, so he talk about the electron is orbit around the nucleus, right? And the first N equal to 1 is what he talk about is ground state. He talk about this is a ground state, which means it's the normal state that the electron is supposed to be. Okay, it's the normal state that the electron is supposed to be. The electron is supposed in the ground state. Okay, without any disturbation, the electron is supposed at the ground state. But remember, how do we make the hydrogen emit light? We apply a very high voltage on the container, the tube, which means we apply the energy on the electron, apply the energy on those on the hydrogen elements. So the electron, once it's being excited or apply energy, they're going to jump, just like you eat too much sugar. What do you feel? Sick? Yeah, you feel very sugar high. Okay, yeah. So the same thing. Okay, you're going to very excited. Again, you cannot stop. So the electron doing the same thing. They're going to jump. Okay, they're going to try to jump from level 1 to the level 2, or even jump in a higher level. Okay, that really depends on how much energy you apply. If you give it really high energy, then the electron will jump. Okay, they're going to jump. Let's see, they're going to jump to the number 4. So the electrons is no more go to the ground state. They're jump to the N equal to 4, level 4. And this level 4, from level 2, level 3 until anything, this area is what we call the excited state. This is what we call the excited state. So when the electron jump from the excited state, then the energy, this represents the electrons has really high energy. Okay, the electrons, they jump. They can either jump to the 2, 3, 4, 5, 6, 7. They cannot jump somewhere in between, because in between those levels, there's no space they can stand on. That makes sense, right? Just like your goal, once you go on the step, I mean, you have to stand on the step. You cannot stand on somewhere between the 2 steps. That makes sense, right? So the electron is doing the same thing. When they jump, they have to jump to a certain level. They cannot jump in between. There's no way to let the electrons stand on in between the levels. Okay, so that is why we find a whole number, because they have to stay to a certain level, and those level is the whole number, right? N equal to 2, n equal to 3, n equal to 4. Okay, and then when the electrons reach to the certain level, but just like when you got a super high, and later what happened? You crashed, you collapsed, and you collapsed. So the electrons is doing the same thing. Okay, so they try to jump back because they are lost their energy. The electron lost their energy, then what happens? They're going to jump back. They're going to jump back. But it doesn't mean the electron will jump back directly, go back to the n equal to 1. Sometimes they can jump back to any other level, as long as it's lower than the highest level they jump. They can go back to level 3, or they can go back to the level 2, or eventually they go back to the level 1. That makes sense? Okay? Yeah. But you see, since different level give you the different energy, when they jump back from higher level to the lower level, then there's an energy difference over there. The higher level has a high energy, lower level has a lower energy. When they jump back to the lower energy, where those energy goes there? Where the energy? They go from high to low, then they have a lower energy. Then where is the energy between those, the gap? That is the energy that is going to release out. And the released energy is electromagnetic wave. Okay, and remember, each of the electromagnetic wave will contain a specific frequency and wavelength. And the wavelength is a fit in between the visible light, which is from 400 to 700, it becomes a visible light that we can see. This is what happened. So when the electron jump from high energy to low energy, they are going to release the heat, release the energy out. They are going to release the energy out. And the part of the released energy fit for the frequency. And this frequency, if the frequency or the wavelength within 400 to 700 nanometer, and that part of the energy, that if we receive that part of the energy, then we can see it, because that's a visible light. Okay, so I hope you can convert the concept. Energy is an electromagnetic wave. Okay, if the energy fit into the visible light range, then we can see. Of course, when the electrons, they jump from 4 to 3, and this level of energy maybe is not, I mean, they're going to also release the energy out. But the point is, this part of the energy too small, and the wavelength is much longer than the wavelength, than the visible light from 400 to 700. And then they probably just release the heat. So that's why if you put your hands around the hydrogen, the emission light, you can feel the heat. This is also, and some of this, maybe from 7 to 1, these electrons, if these electrons jump to 7, they go back to number 1, they release much more energy. And this energy has a really, really small wavelength, which is not fitting 400 to 700, maybe fitting to the UV light. And then you cannot see that, right? So in another word, some of the energy, when the electrons jump back, the hydrogen release the heat. And some of the heat, we capture those heat, and that's fit into the visible light. But there are some other heat or some other energy that we cannot see. Maybe fitting the UV light, maybe fitting the visible, the ultraviolet, UV light and infrared. Does it make sense? That makes sense? Darren? Okay, so this is what happens. Yeah, this is a very true over here. The reason we can see the light is because the electrons is being excited and then they jump back, and some of the energy they released that we can catch up. We catch those energy, and this energy is the visible light. And this is also explained why for hydrogen we can only see the 4 line shows up there. That's because those energy they jump, only those energy jump from 4 to 2, 3 to 2, 5 to 2, 6 to 2 can be those energy that we can catch. And those energy with the wavelengths fitting from 400 to 700 nanometer. That is why. Okay, yeah, so this is another hydrogen spectrum of there. You see, only there's a series from 3 to 2, 4 to 2, 5 to 2, 6 to 2, and only those 4 lines can be catched by our eyes. For the rest of other energy that are released, we cannot see. For example, the Lyman series, those energy from 2 to 1, 3 to 1, 4 to 1, 5, 6, 7 to 1, those energy that are released has a too high energy, then we cannot catch it. Those are released is UV light. Okay, yeah. And if you're talking about those things, when they release, the energy is too small, and also we still cannot catch. Those are fitting into the infrared. Okay, yeah. So generally, visible light is defined by our human eyes. It doesn't mean if it's maybe some specific people with the ability to see more higher range of the color. That's possible. I don't know, right? Just like the snake can detect the infrared and not, right? Yeah, they can see higher range of this, right? Some of this, the bat can receive like a radio wave, so they can locate. This is also their function, but our human eyes can only see the range around 400 to 700. Okay, yeah, I'm talking about 400 to 700. It doesn't mean it's exactly 400 to 700. It's above this range, so the human being can see it. Okay, that's interesting, right? And also, this is I'm talking about. This is also what I'm doing the research. When we talk about the aurora is also what happens. Is because of that. Okay, so I think everyone see the aurora. You can see the aurora over there, right? Aurora. So this is aurora. And aurora, they also has a different light shows over here. And remember, the reason the aurora has the color, you can see it, is because of the elements in the sky, they are excited. Okay, just simply introduce a little bit, okay, since I'm doing this research. Our Earth, this is our Earth, right? And let's see the sun. This is a sun. Sun is going to be much bigger than Earth. So the sun is going to shoot some of the particles to the Earth. I'm talking about the particles, not just the light. It's not just the light. When the sun shooting the particles, it's not just a light. Could be something else. Okay, could be something else. It has a very high energy particles. Maybe it's containing hydrogen, maybe containing electrons or something else. Very high energy particles. And just to let you know, and also they have a UV light for this. Generally, those are particles, high energy particles, so we give its name. It's called a solar wind. Have you heard of the solar wind before? Right, solar wind. So solar wind is just like the wind, but the wind, you feel the wind is because we have air, the air particle shooting at your face. So you feel the wind, okay? But the sun also shoots some of the particles, but you are not going to, you don't want to receive that. Those particles has a really, really high energy, okay? So when we expose it, we die, okay? We die. So, but the good things, okay? So give thanks to the earth. They have a very, very good function to protect the earth. One thing is they have a, you know what is this? Earth has a very good magnetic field. Has a very good magnetic field. Okay, so when those charged particles, when they shoot at the magnetic field, then they are going to changing the direction, the flying direction. This is what happened for the charged particle. If there's no charge, then they're going to penetrate through the magnetic field. But once they have the charge, they're going to change the direction. So instead, they directly shooting on the surface of the Earth, then they're going to travel aligned. They're going to travel align the magnetic field. So then eventually they're going to merge into the polar area, North Pole or South Pole. That makes sense, right? That makes sense, right? So, and also give thanks to the area. In this area, we have a lot of gas. I mean, we have air. This area, definitely we have a nitrogen, and we have oxygen, and also we have ozone over there, right? So those charged particles, so they're going to first shoot at those the air particles first. Again, those are high energy stuff. When they shoot those particles, what happens? They give it energy to those particles. So they're going to excite it. And the electrons inside of the nitrogen, the oxygen, ozone, and even we have hydrogen over there. They're going to excite it. So when those particles are cooling down, they're going to emit light. And those lights is what we call the aurora. Okay, different particles may represent the different color. Nitrogen is generally making the green color. Okay, I'm not sure what is the pink color represent for, but they are going to emit the light, and this light is what we call the aurora. Meanwhile, it's not just the heating emit the visible light. They're going to emit something else. Okay, like infrared or the UV lights. They're going to emit those things also. So when they emit this, the satellite on the outside of the Earth will receive those signals, and then we can determine where the aurora boundary is. So this is a very interesting topic, and this is since this is related to what I'm talking about here, so that's why I just gave you a little bit introduction. Okay, so I think I'm done over here. Today we're just talking about how we can see the light. So next time we're going to talk about the quantum mechanics plus the electron configuration. How many of you heard about the electron configuration? Okay, we will talk about the electron configuration next time. Okay. And then in the lab time, remember, we're going to doing the calculation for the for the lab 50. Okay, and if we have more time, I'd like to do the review for the exam. Okay, exam break. Okay, so I will see you next Monday.
You know when you might have those posted?
The grade?